There's a myth going round town that when you get older you just sit down and start rocking, just rocking. In a way that's true, if you know what I mean. Just take a look at the senior scene. Well, it's rocking.
This is a two-day program, and the first day, the topics that I want to cover are what is science and the scientific method, how are weather and climate different, how does the atmosphere work, the history of meteorology and atmospheric science, and then just an example of one of the impacts that man has had on the atmosphere and how we've dealt with it was the ozone depletion problem. That was a big problem in the 70s and is still a problem today, but we seem to have been able to accomplish some things in that area. So the purpose of the workshop today is basically to discuss climate change and give you the tools that you need to basically understand what climate change is about and why we think this is a problem and why we think it's occurring. So I just pulled a couple of definitions. The second one I just made up. Science can be considered the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. It's also a method to understand the past, predict the future, and utilize the present.
It's easier.
So if you think about science, science as we understand it really began in the in the 16th and 17th century, in the Renaissance. And Isaac Newton was one of the first ones to publish a work detailing physical laws about the universe. And the laws of motion that established basic physics for the last, until Einstein, basically were the laws of physics for the known universe. So in 1687, Newton published the Principia Mathematica, which described these laws and universal gravitation. If you go up to the 18th century, you saw a huge rise in scientific experimentation. You have people like Benjamin Franklin who are doing scientific experiments. You get the beginnings of chemistry and geology and biology. In the 19th century, you get the beginnings of scientific philosophy and the understanding of electromagnetism and atomic nature of matter. And then in the 20th century, we have things like theories of general and special relativity, quantum mechanics and astrophysics, and all sorts of things that have made our civilization where it is today. So if you think about what the basic principles of science are, there are two very basic principles that came out of the philosophy of science in the 1800s. And they were really thought of or put in writing by Charles Lyell, who was a geologist in England. And the first one is the uniformity of law across time and space. And basically saying that natural laws are constant across space and time. This gives you the ability to be able to understand the past and predict the future, because if things are changing all the time, you really can't understand the past or the future. And then the uniformity of processes across time and space, that natural processes are constant across time and space. So the laws of physics remain the laws of physics through all time. Then this isn't Lyell's, but it's a common addition to the basic principles of science, at least the way a lot of science is thought of, though it's not as imperative, is Occam's razor, that the simplest solution is most likely to be the right solution. And there's now some thought that might not be the case, say, in quantum mechanics and some other more complex theories about the nature of the universe that may be more complicated reasoning, that things aren't going to boil down to simple E equals mc squared, which you had with Einstein. The scientific method generally is accepted that there are basically 6 parts to it: observation, questioning, generating a hypothesis, doing experiments to test your hypothesis, determining what the results are of your experiments and developing a conclusion from the results of the experiments. But this process doesn't have to go in this order, and it can be iterative, that you can repeat it numerous times. And then one of the really important parts of the scientific method is that everything that you do is subject to testing and evaluation by others. So that what you do has to be repeatable, and it can be challenged and verified or not verified by other scientists. So typically science is in terms of theories. It's very hard to produce something that goes beyond the theory, because essentially most accepted knowledge, say like Newton's laws would be a great example, were the fact until somebody was able to disprove them, which was what Einstein did with special and general relativity. And he was just able to expand on Newton's laws and show that Newton's laws only work in a particular range of circumstances, in the range that we commonly occur. But when you look at intergalactic types of experiences, and when you look at astrophysics, they no longer work, because then the speed of light and other factors become important to understanding the basic laws of motion. Weather is a mix of events that happen each day in our atmosphere. The weather changes with location and time. Weather is different in different parts of the world and changes over minutes, hours, days, and weeks. Most weather happens in the part of the Earth's atmosphere that's closest to the ground, which is called the troposphere. There are many different factors that can change the atmosphere in certain areas, like air pressure, temperature, humidity, wind speed, direction, and lots of other things. And together they determine what the weather is like at a given time and location. So climate describes what the weather is like over a long period of time in a specific area. Different regions can have different climates. To describe the climate of a place, we might say that the temperatures are like during different seasons, how windy it usually is, and how much rain or snow typically falls. When scientists talk about climate, they're often looking at averages of precipitation and temperature, humidity, sunshine, wind, and other measures of weather that occur over a long period in a particular place. So in some instances, the typical is take 30-year average. And it can be a rolling 30-year average, so as the weather gets warmer, you'd encompass the new years into that 30-year average, so the average for the 30 years would constantly get warmer, so the climate would be changing. Climate provides a sense of what to expect, but doesn't provide any specific details about what weather will be on any given day. It just gives you a range. Looking at climate normals, and normals being a 30-year average, can help us describe whether the summers are hot and humid, or whether the winters are cold and snowy at a particular place. They can also tell us when we might expect the warmest day of the year or the coldest day of the year at a given location. Anybody here gardeners or farmers?
Yep.
Yeah, because I mean everybody knows that the growing the growing season getting longer, and also I forgot the term for this, but the country's divided up into 8 temperature zones for growing plants, and those areas are changing and moving further north. The warm weather areas are moving further north, so you can actually see that in our lifetime. So just going back about a brief history of meteorology and atmospheric science, thought about the weather as been present for as long as we've had history, basically. It goes back to 3,000 years or more in writing in India. And it was present in Greeks and the Romans and the Egyptians and everybody else that you could think of. But it wasn't until the 17th century where we really started making instruments and taking measurements. And Galileo was one of the first people to build a weather instrument. And you had the barometer being invented in 1643, and Edmund Halley at the end of the 17th century was the first to identify that it was solar heating that was providing the energy to power the atmosphere and cause atmospheric motion. In And then in the 18th century, you had Fahrenheit and Celsius developing as scales for temperature, and you had a lot more meteorological measurements being recorded, and the beginning of trying to predict the weather. And in the 19th century, you had a big increase of that. You had weather mapping and prediction beginning to take place. Basic atmospheric laws are being developed, the laws of thermodynamics, kinetic theory of gases, the ideal gas law, and all the laws that were subsumed in that. I don't, unless people want me to, I'm not going to go over the details of the laws. But the basic law of the ideal gas law is PV equals nRT, which basically shows the relation of pressure and volume to the amount of molecules, the temperature, and a constant. The layers of the atmosphere discovered in the 20th century, which goes back to the troposphere and the other layers. The atmospheric modeling begins, and satellite measurements of the atmosphere and global storm tracking actually begin in 1959 with the first meteorological satellite. So as we were saying, now we can predict hurricanes, and a lot of that is due to the fact we have satellites in space that can look at global wind patterns and watch storm development. Now, just to give you, some other, it's about depth. You're seeing that the height of the troposphere, which is where most of the atmosphere is 6 to 7 miles on average. The diameter of the Earth is almost 8,000 miles. The distance to the moon is almost 240,000 miles. The average depth of the ocean is 2.3 miles. The maximum depth is almost 7 miles. So the maximum depth of the ocean is almost as deep as the troposphere is tall. So the atmosphere is a pretty thin layer around the Earth, but it does protect life and provides a shielding from radiation that would otherwise cause a lot of harm, and gives us weather and makes the Earth habitable. So atmospheric circulation. Is everybody aware of how the globe, that air is constantly circulating around the globe? So that pollution that is generated in China, for example, can reach the United States. And, a lot of the work that was done to look at global air motion was actually a result of our atomic testing program. Because people were tracking nuclear radioactive material in the atmosphere, and that way they could actually determine where materials were coming from all around the globe, because you blow up a bomb and then you'd measure radiation on the other side of the planet, and you could track it and see how it all moved around. So there are several models, and one of the simpler models, it involves a bunch of different cells, large cells that essentially cover about 30 degrees of latitude. So around the equator you have what's called Hadley cells, and in Hadley cells, because of heating, the air is rising. And then it goes up near the equator and then comes down around 30 degrees north and south latitude. And then in the mid-latitudes, from 30 to 60 degrees, you have what's called the Ferrel cells. And then in the polar regions, from 60 to 90 degrees, you have the Ferrel cells. And this is just these recirculatory patterns, and they're very general, that essentially move air north and south. So, and then there is some migration across the equator, but both the north and the south hemisphere have somewhat isolated weather systems. The next thing I wanted to talk about briefly is solar radiation and the Earth radiation. And so both the sun and the Earth are radiating. And anybody here know what black body radiation is? No. And I wouldn't, it's a somewhat difficult concept, but it's a concept that every object radiates heat, or let's not put it that way. Every object radiates light based on its temperature. And if an object is at, say, 6,000 degrees, which is the temperature of the surface of the sun, it has a signature radiation pattern that it produces light in that range, both visible and not visible light. The Earth being at, say, 20 degrees, or say 55 degrees would be the global norm, produces black body radiation at that temperature. And because it's at a much lower temperature, it radiates in the infrared portion of the spectrum. Most of your higher frequency light or lower wavelengths, is eliminated by the atmosphere, which is great because otherwise we'd be fried. So if you look at the Earth's energy balance, what comes in has to go out, or else we just start cooking. And we get warmer and warmer and warmer. And we're in a sort of semi-equilibrium. And normal situation, the climate wouldn't be changing, and essentially you're in an equilibrium situation where the same amount of energy that's coming in is also going out. Right now, because of the greenhouse effect, we're essentially starting to heat up the atmosphere a little more, and we're changing that equilibrium point. So if you look at this, this basically shows you that, on a scale, that 341 watts per square meter of energy is coming in from the sun, where 101 watts per square meter is being reflected from the atmosphere. And the term for the reflection is the albedo of the atmosphere, which gives you the reflectivity. And the same thing is true for the Earth's surface, is that the Earth's surface also reflects energy back into the atmosphere and back out into space. But some of the energy that's reflected off the surface of the Earth is absorbed by the atmosphere, and some of it goes out into space. So the composite has to essentially equal. So if you add the 102 to the 239 of outgoing radiation that's emitted by the atmosphere, it comes out to the 341 that's coming in, which is nice, so we're not gaining heat constantly. Air quality is a state of the atmosphere with the chemical substances at a given place and a given time. So when you hear that air quality is good or bad, that basically is a measure of the chemistry of the atmosphere at a particular location and time. Atmospheric chemistry basically deals with understanding all the chemical composition of the atmosphere, and air pollution is essentially materials that are in the atmosphere that at a not normal level. And air pollution can be caused by people, and it can be caused by nature. But then when you look at what, man-made, we have all sorts of industrial pollutants that are put into the air from industry, from generating power, from, just our transportation. Right, automobiles, right, all sorts of combustion.
Cutting down all the trees.
Right, cutting trees, and trees are one of the ways that pollution tends to be removed from the atmosphere.
Right.
So when we cut them down, then essentially pollution can become elevated.
Right.
So, I was going to talk about this for the next few minutes before we call it a day. And this is, I think, a really good example of a situation that was a global problem that we had back in the 70s, and that we had in the 70s, that was essentially hypothesized or detected in the 70s by these three gentlemen who won the Nobel Prize for their work in essentially ozone depletion. And what they did, this was Sherwood Rowland, Mario Molina, and Paul Crutzen in Germany, was they recognized that we might be causing a problem in the stratosphere because we were releasing a set of compounds that could essentially destroy the ozone in the stratosphere. And the amount of ozone in the stratosphere was beginning to decline. And they were smart enough to realize what might be causing it and recognize what might be needed to be done about it. So first off, this is a picture of the atmosphere in relation to ozone. And we're only looking at the troposphere and the stratosphere. So the troposphere goes up 6-7 miles, and the stratosphere goes up the rest of the way. And you can see that the ozone is largely in the troposphere. Now we do have surface ozone that's created by air pollution. So like when you hear the EPA or somebody else say that we're having a high ozone day, that's surface ozone, not stratospheric ozone. So the ozone in the atmosphere is, in the lower atmosphere, in the troposphere, that we breathe is caused by photochemical smog, essentially. And photochemical reactions in the atmosphere produce the ozone. So we've done a lot in this country to control ozone levels by lowering nitrogen oxides and other gases, hydrocarbons, that were the cause of the ozone being generated in the troposphere. Now in the stratosphere, typically because of the temperature profile that I showed earlier, the air in the stratosphere and the air in the troposphere don't tend to mix very much. And some material does migrate gradually up into the stratosphere, but it takes a long period of time, and it's typically only stuff that's relatively inert that can excuse me, another drink. It's only compounds that are relatively inert that can last long enough, on the term of 1 to 5 years, to migrate into the stratosphere. So, and in the stratosphere you have this ozone layer which is being generated by the impact of UV radiation, ultraviolet radiation, on oxygen molecules. The UV radiation is powerful enough that it does what's called dissociates the oxygen in the oxygen molecule. Oxygen in the atmosphere is a dimer. It's 2 oxygen molecules bound together. And what the ozone does is it affects that bond between them, breaks them apart, and then one of those radicals, becomes an ozone radical, attaches to another ozone molecule, oxygen atoms attaches to another oxygen molecule, and so now you have 3 of them and that becomes ozone. So 3 oxygens bound together is ozone. 2 oxygens is what you're normally breathing, and 1 is an oxygen radical because it has what's called a free electron. Okay, so if you look at the ozone layer, what was happening, what they recognized was that gases were getting up into the stratosphere and potentially decreasing the amount of ozone that was there. So what's the function of ozone in the atmosphere? Well, we've talked a little about it, but basically it absorbs a portion of solar radiation, essentially the ultraviolet portion of UVB, which is a high frequency ultraviolet. And that type of radiation is linked in humans to skin cancers and eye cataracts. And also, in general, it can harm crops and harm marine life because, again, it's high energy. It's also what causes, skin burns, that in UVA. So, it's not a good thing for the ozone level in the stratosphere to decrease because it allows all these harmful rays of ultraviolet to get down into the troposphere, down to the surface. So Rowland and Molina hypothesized that stratospheric ozone was being destroyed by fluorine and chlorine free radicals that were created by the photolytic decay of chlorofluorocarbons and other compounds that essentially could reduce the amount of ozone. And that this was a catalytic process so that when these compounds decayed, the product that they produced didn't just get reacted with and taken out of the atmosphere, it just continued to react with additional molecules of ozone and destroying lots of ozone. And then lastly, that the reduced ozone would allow more UV radiation to reach the ground and cause all the problems that we were just discussing. So this is why this was a really substantial problem that was identified. So what needed to be done? Well, we needed to reduce the amount of chlorine, fluorine, and bromine reaching the stratosphere, which meant we needed to eliminate the most destructive ozone-depleting substances, which we'll call ODSs. And these are compounds that are generally very stable in the troposphere that only degrade under the intense ultraviolet light once they hit the stratosphere. And these compounds tend to be things like the chlorofluorocarbons. Anybody know how chlorofluorocarbons are used? What they're typically called? What?
In refrigerants.
Right, refrigerants. They're freons. And they were, very popular refrigerants in the 60s and 70s. And they were not generally natural compounds. These were man-made materials that we were using for refrigeration because they were relatively inert, could be compressed and then expanded to cool whatever we were trying to cool, which is how the refrigerators and air conditioners worked. These three guys recognized that in order to control the loss of ozone in the stratosphere, we had to develop a control strategy. So, just to give you an idea, one of the things that was detected early on was that we were generating what was called an ozone hole, and this was over Antarctica. And because of the cold temperatures there, it was especially sensitive to loss of ozone. Basically, lots of people were testing and evaluating Roland Molina's hypothesis, and nobody was able to invalidate it. So there was a big conference, an international conference in Vienna, and then after that came a treaty that was done in Montreal, the Montreal Protocol, where all the nations pledged to reduce their use of the freons and substitute other chemicals that will be less problematic for destroying ozone. So, and then you can see over the last couple of decades, there have been additional versions of the reports and additional adjustments to the programs to diminish the fluorocarbons that are being introduced in the atmosphere. Has anybody noticed, for example, how the freons have been changing over the last 30 years? No, I mean, if you would try and run an air conditioner that you had back in 1960, it wouldn't work today because they use different freons. And the same thing is true for air conditioners 1970, 1980, 1990, 2000, and even 2010. They keep changing the freons to freons that are
That's right.
essentially less of a problem in generating ozone. So the point was that through these global treaties and all the efforts that have been made, we've actually made an impact on how much ozone is in the stratosphere, that we've actually curtailed to a large degree these problems. If we keep doing what we've been doing, the problem will diminish over time.
We paid our dues all those years, and it's so nice to be switching gears. It's a grand new century, and it's the senior life, the senior life, the senior life for me.